By 1942, the air war over Europe has reached a dead end. Thousands of bombers cross the skies. Cities burn. Factories are hit again and again. And yet the heart of German industry keeps beating. The reason is simple. It has gone underground. Railway tunnels disappear into mountains. Submarine pens are buried beneath meters of reinforced concrete. Factories are relocated into hillsides, caves, and deep shafts where ordinary bombs cannot reach. Conventional bombing doctrine begins to fail. Even the largest standard bombs explode on the surface, shattering roofs and walls but leaving foundations intact. Repair crews move in within days. Production resumes. The damage is visible, but not decisive. German engineers have built structures designed to endure earthquakes, artillery fire, and near misses. Concrete roofs several meters thick, shock-absorbing layers, massive foundations anchored directly into bedrock. For Allied planners, this creates a terrifying realization. There are targets that cannot be destroyed from the air, at least not with the weapons that currently exist. Attempts to increase bomb size bring new problems. Larger bombs are inaccurate, slower, impossible to carry by most aircraft. Dropping more bombs only increases destruction on the surface, not beneath it. The war demands something different, not more explosives, not more aircraft, but a new way of thinking about force itself. What if the goal is not to break the target, but to break the ground beneath it? What if destruction does not come from blast and fire, but from shock, vibration, and collapse? These questions circulate quietly through British engineering circles, largely dismissed as impractical or unrealistic. Yet the problem refuses to go away. As long as German industry can hide underground, the war will continue. And so behind closed doors, a radical idea begins to take shape. One that will challenge every assumption about bombing, physics, and what an aircraft can deliver. The solution will not flatten cities. It will make the earth itself turn against what is built upon it. The idea does not come from a bomber commander. It does not come from a general, an admiral, or a politician. It comes from an engineer. Barnes Wallis has spent his career solving problems that others consider impossible. Airships, geodesic aircraft structures, mathematical stress calculations that push materials to their absolute limits. To Wallis, the problem of underground targets is not strategic, it is mechanical. He studies bomb damage reports with an engineer's eye. Surface explosions, shattered roofs, intact foundations. He sees the same pattern repeated again and again. The energy is being wasted. A bomb explodes in air or on impact, throwing force outward. Most of that energy dissipates uselessly into the atmosphere. Concrete absorbs what remains. Wallis asks a question few others are willing to consider. What if the bomb does not explode on the surface at all? What if it goes through the earth first? In his calculations, destruction does not come from blast or fire. It comes from shock transmission. A deep underground explosion sends seismic waves through the surrounding rock, undermining foundations, cracking concrete from below, and collapsing structures that remain untouched from above. Not a bigger explosion, a smarter one. Wallis calls it an earthquake bomb. The idea is radical, almost heretical. To make it work, a bomb would need to fall from extreme altitude, accelerating to near supersonic speed. It would have to penetrate deep into soil or rock before detonating. It would need an entirely new shape, weight, and internal structure. The bomb would be massive, so massive that existing aircraft could barely lift it. Military planners react with skepticism. The bomb is too large. Too expensive, too specialized. Accuracy is questioned, risks are highlighted, resources are scarce. But Wallace persists. He produces calculations, diagrams, and test data. He argues that near misses do not matter, that even a detonation tens of meters away would cripple a target by destroying what holds it up. Slowly, reluctantly, interest grows. Not because the idea is comfortable, but because nothing else is working. The war has reached a point where conventional answers are no longer enough. And in quiet offices, far from the sound of engines and gunfire, the most dangerous bombs of the war begin as equations on paper. Barnes-Wallace concept is not built on intuition. It is built on mathematics. Traditional bombs are designed to explode on impact or shortly after. Their destructive power comes from blast pressure and fragmentation, spreading outward in all directions. Against buildings, this is effective. Against the earth itself, it is wasteful. The ground absorbs energy. Concrete deflects it. Most of the explosion vanishes into the air. Wallace approaches the problem differently. He calculates what happens when a massive object falls from extreme altitude. Accelerated by gravity alone, a bomb dropped from over 20,000 feet reaches near supersonic speed before impact. At that velocity, steel does not shatter on contact, it penetrates. The bomb does not strike the target, it dives into it. Soil, clay, and even rock behave briefly like fluid under such forces. The bomb punches downward, burrowing deep before its delayed fuse triggers detonation. The explosion does not vent upward, it is trapped. And trapped energy has consequences. The underground blast generates powerful seismic shock waves. These waves travel through the earth faster and more efficiently than surface blast. When they reach foundations, they do not crack walls. They remove support. Buildings collapse not because they are broken, but because the ground beneath them has failed. A direct hit is no longer required. A detonation meters away can achieve the same result. Wallace proves this with scale models, calculations, and controlled tests. He shows that the deeper the explosion, the more destructive the shock transmission becomes. Paradoxically, a bomb that explodes unseen can cause more damage than one that obliterates everything on the surface. This is why accuracy becomes secondary. The bomb does not need to strike the bunker. It needs only to land near it. But physics demands a price. To penetrate deeply, the bomb must be long, dense, and extremely heavy. It must be strong enough to survive impact without deforming. It must fall straight without tumbling. Even slight instability would ruin the effect. Every variable matters: shape, weight, spin, altitude, velocity. The margin for error is small, yet the calculations hold. If the bomb can be built, if it can be delivered, then no structure resting on the earth can truly be safe. Turning theory into metal is where most radical ideas fail. The earthquake bomb is no exception. By 1943, Barnes-Wallace calculations have convinced enough officials to allow development to begin. But immediately, reality intervenes. This is not just a bomb. It is an engineering problem unlike anything attempted before. The weapon must be long and narrow, built to survive near supersonic impact without shattering. It must fall perfectly straight, without tumbling or yawing. Any instability would rob it of penetration and turn it into just another oversized bomb. The result is Tallboy, over 5 tons of steel and explosive, stretched into a sleek, almost elegant shape. Its casing is so thick that it is forged in a single piece, heat-treated to withstand impact forces no conventional bomb could survive. Even the explosive filling is different. Torpex is chosen for its power and shock effect, not for surface blasts, but for the violence of its underground detonation. Every design choice serves a single purpose: deliver energy into the earth, not the air. But building the bomb is only half the battle. Tallboy creates problems for everything around it. It is too heavy for most bombers, too long for standard bomb bays, too demanding for existing release mechanisms. Entire aircraft must be modified just to carry it. Accuracy becomes another concern. Tallboy must be dropped from extreme altitude to achieve the required penetration velocity. That means long exposure to enemy defenses and minimal margin for error. Crews must fly straight and level for seconds that feel like minutes. Testing reveals more complications. Early drops show instability, slight oscillations, minor deviations that could mean failure in combat. Engineers adjust tail fins, mass distribution, and spin characteristics until the bomb finally falls true. When it does, the results are undeniable. Test detonations shake the ground for hundreds of meters. Concrete structures crack from below. Targets that appear untouched suddenly collapse inward as their foundations fail. The bomb does not announce itself with fire. It announces itself with silence, followed by collapse. Tallboy is no longer a concept, it is real. And for the first time in the war, Allied planners hold a weapon capable of destroying targets that were never meant to be destroyed from the air. Tallboy cannot be carried by just any aircraft. Its weight alone disqualifies most bombers in Allied service. Its length exceeds standard bomb bay dimensions. Its release demands absolute stability at extreme altitude. To deliver the earthquake bomb, the aircraft itself must change. The Avro Lancaster is chosen not because it is perfect, but because it is the only platform with the potential to become perfect. Engineers strip the aircraft of anything not essential to survival and flight. Armor is removed, defensive guns are reduced, crew numbers are cut. Every kilogram saved is reassigned to a single purpose: lifting one massive bomb high enough, fast enough, and far enough. The bomb bay doors are removed entirely. Tallboy does not fit inside the aircraft. It hangs beneath it, exposed to the airflow, altering handling characteristics and increasing drag. Pilots immediately feel the difference. The Lancaster becomes slower to climb, less forgiving, and far more demanding to fly. Flight profiles are rewritten. Crews trained to reach extreme altitude with a single bomb instead of the full load. Engines are pushed to their limits. Fuel margins shrink. There is no redundancy. One engine failure means aborting the mission, or worse. The aircraft is no longer a bomber in the traditional sense. It is a delivery system. Navigation becomes critical. Bomb aiming becomes simplified but not easier. The aircraft must fly straight and in level during the drop, holding course while enemy flak reaches upward, unopposed by heavy defensive fire. There will be no second pass. There is no margin for improvisation. Each mission revolves around a single moment. Release. When the bomb finally drops, the Lancaster immediately climbs away, lighter by 5 tons, suddenly responsive again. Crews describe the sensation as being released from a physical grip. The aircraft survives by not lingering. Tallboy missions are not mass raids. They are solitary strikes. Few aircraft, few bombs, singular objectives. In this role, the Lancaster ceases to be part of a bombing stream and becomes something else entirely: a precision instrument built to deliver one overwhelming blow. And once the crews master this new way of flying, the weapon system is complete. Aircraft and bomb no longer exist separately. They operate as one. The first operational uses of Tallboy are not spectacular. There are no firestorms, no cities erased from maps, no immediate proof visible from the air, and that is precisely the point. Tallboy is aimed at targets that have survived everything else. Submarine pens along the Atlantic coast, railway tunnels driven deep into mountains, hardened factories carved into hillsides where German production continues untouched by conventional bombing. When the first Tallboy missions are launched, expectations are cautious. Crews are warned that success may not look like success. There may be no visible damage at all. Then the bombs fall. From extreme altitude, Tallboys accelerate downward, striking the earth at near supersonic speed. They vanish into soil and concrete, leaving little more than a scar on the surface. Seconds pass, then the ground moves. Entire sections of reinforced concrete crack from below. Tunnel ceilings collapse inward. Structures that appear intact suddenly sag, tilt, or sink as their foundations fail. In some cases, Tallboy misses its target by tens of meters. It does not matter. The shock travels through rock and soil, breaking what cannot be repaired. Tracks twist inside collapsed tunnels. Machinery buried underground is thrown out of alignment. Precision tools are ruined without ever being directly hit. German engineers are stunned. Damage assessments reveal something new. Destruction that cannot be patched, replaced, or bypassed. Repairs take months, not days. In some locations, repairs are abandoned entirely. Submarine pens that once laughed at Allied bombing are rendered useless not by penetration, but by distortion. Doors jam, cranes fail. Dock floors crack unevenly, preventing vessels from entering or leaving safely. Factories go silent without being visibly destroyed. Production stops underground. Tallboy has proven its purpose. It is not a weapon of spectacle. It is a weapon of permanence. Word spreads quickly through German command channels. Engineers warn that no amount of concrete can protect against this kind of attack. The ground itself has become the enemy. For Allied planners, the conclusion is immediate. The earthquake bomb works, and now that it has proven itself, its targets will grow larger and more ambitious. Tallboy proves the concept, but for Barnes-Wallis, it is still a compromise. Even as the first targets collapse underground, he knows there are structures Tallboy cannot fully defeat. Bridges anchored deep into bedrock, massive viaducts, reinforced facilities built not just to resist bombs, but to survive partial collapse. To break those, the logic must be taken to its extreme. The answer is not refinement, it is escalation. The new bomb will not weigh 5 tons. It will weigh 10. Grand Slam is conceived as the ultimate earthquake weapon. A bomb so heavy, so dense, that penetration alone will guarantee catastrophic shock transmission through rock and concrete. Its casing is even thicker than Tallboy's, forged to survive impact forces that approach the limits of steel. Its shape is optimized for stability at extreme speed. Everything unnecessary is stripped away. This is not a bomb designed to explode violently. It is designed to force the Earth to fail. The challenges are immense. No existing aircraft can carry it without radical modification. Only a handful of Lancasters are capable, and even they must be stripped to their absolute minimum. Fuel margins become razor thin. Climb rates are sluggish. Any mechanical failure means disaster. Each Grand Slam mission becomes a singular event. One aircraft, one bomb, one target. There will be no second attempt. Training intensifies. Crews rehearse endlessly, knowing that a single error in altitude, speed, or release timing will turn the weapon into useless scrap. When Grand Slam is finally dropped in combat, the effect surpasses expectations. Targets do not simply crack, they collapse. Massive bridges sag and twist, their supports torn from the earth. Underground facilities implode from within. Shock waves propagate outward, damaging structures hundreds of meters away. German engineers quickly realize the truth. There is no countermeasure, no thicker concrete, no deeper foundation, no redesign. Grand Slam has crossed a threshold. It is no longer a bomb meant to destroy a target. It is a weapon meant to deny the ground itself. And once it enters the war, nothing built on solid earth can truly be considered secure. For years, certain German targets were considered untouchable, not merely hardened, but permanent. Bridges sunk deep into riverbeds, viaducts anchored to bedrock, submarine facilities designed to survive direct hits from the largest bombs Allied aircraft could carry. They were not meant to be defended. They were meant to endure. Tallboy and Grand Slam change that assumption completely. When these weapons are used against heavily reinforced bridges, the results defy traditional damage assessment. The spans are not blown apart, the superstructures remain partially intact, but the ground beneath them no longer holds. Shock waves propagate through soil and stone, shifting foundations by centimeters, enough to make precision engineering collapse. Bearings jam, pylons tilt, load paths fail. A bridge that looks standing is suddenly unusable. Rail traffic stops instantly. In some cases, the entire structure slides sideways into the river without dramatic explosion, collapsing under its own weight as the earth rearranges itself beneath it. Submarine facilities suffer the same fate. Pens designed to withstand repeated bombing find their floors cracked and distorted. Dock levels change unevenly. Heavy machinery loses alignment. Doors no longer seal. Cranes jam permanently. The bunker still stands, but it no longer works. This is the true power of the earthquake bomb. It does not need to destroy what is visible. It destroys what is essential. German repair crews face a nightmare scenario. There are no replacement foundations, no quick fixes, no way to realign structures built on damaged ground. Entire facilities must be abandoned. The psychological effect is immediate. Reports from German engineers warn that even near misses now carry catastrophic consequences. Commanders learn that dispersal and concealment offer no protection. Even rumor of an earthquake bomb attack can halt operations. For the Allies, the message is clear. Targets once placed at the bottom of priority lists are now vulnerable. No structure is beyond reach. No amount of concrete guarantees survival. Tallboy and Grand Slam have broken not just physical defenses, but confidence itself. The most powerful effect of Tallboy and Grand Slam is not measured in craters. It is measured in silence. Deep underground, far from the sound of engines and explosions, German engineers and workers begin to understand that the rules have changed. Structures once believed immune now carry an invisible vulnerability. The earth itself can betray them. After the first strikes, reports spread quickly through technical and military channels. Facilities that appear intact above ground are rendered useless below. Floors shift, shafts deform. Precision machinery falls out of alignment beyond repair. And worse, the damage is unpredictable. There is no safe distance. A bomb does not need to hit the target. It does not even need to be close. The uncertainty becomes paralyzing. Engineers cannot calculate safety margins when the ground itself becomes a weapon. Production schedules collapse. Entire underground plants are evacuated after near misses. Crews refuse to return to galleries and tunnels where the walls have begun to crack silently, days after the attack. The fear is not of fire or debris, but of sudden collapse without warning. German commanders face a new problem. They cannot defend against this weapon. They cannot intercept it reliably, and they cannot reassure the people working beneath the surface. Even rumors of Tallboy or Grand Slam missions are enough to halt operations. Rail traffic pauses, submarine construction slows. Repairs are delayed indefinitely as inspections stretch on, searching for damage that may not yet be visible. The psychological impact spreads faster than the bombs themselves. Facilities once considered strategic assets become liabilities. Concentration underground, once a strength, is now a weakness. Every deep structure is a potential trap. The Allies understand this effect well. They do not need to strike every target. They only need to prove that no target is safe. By early 1945, Germany's underground advantage has evaporated. The war has followed industry beneath the surface and found it there. Tallboy and Grand Slam have done more than destroy structures. They have destroyed certainty. And in the final months of the war, that loss proves irreversible. Tallboy and Grand Slam arrive late in the war, too late to change its outcome, too few in number to reshape strategy on their own. And yet, their impact reaches far beyond 1945. For the first time in history, air power proves it can destroy targets not by overwhelming force, but by understanding structure. Not by flattening cities, but by breaking what holds them up. The earthquake bomb represents a fundamental shift. War is no longer about how much explosive can be delivered. It becomes about where energy is applied. Barnes-Wallace's concept survives the war precisely because it is not tied to a specific enemy or battlefield. The principle is universal. Any structure resting on the earth can be undermined if the ground itself is turned hostile. After 1945, this lesson is not forgotten. It becomes doctrine. Cold War planners study Tallboy and Grand Slam carefully. Their data feeds directly into the development of deep penetration weapons designed to destroy missile silos, command bunkers, and hardened underground facilities. The lineage is clear. Modern bunker-buster bombs do not descend from city killers or carpet bombing. They descend from earthquake bombs. Precision replaces mass. Physics replaces spectacle. Tallboy and Grand Slam also mark the end of an illusion, the belief that any structure can be made invulnerable, that concrete alone can guarantee safety. After 1945, no engineer can claim absolute protection. Every design must consider not just blast resistance, but ground failure. In that sense, these bombs do not merely destroy targets, they reshape engineering itself. Today, Tallboy and Grand Slam rest in museums and archives, enormous and silent. Their size still shocks. Their simplicity still intimidates. They were not weapons of terror. They were weapons of inevitability. They did not burn cities. They made the ground give way. And in doing so, they quietly closed one chapter of warfare, while opening another that still defines how wars are fought beneath the surface of the modern world.